This video is going to be on optimization problems. So first we're going to write down a list of hints of what will make these problems a little bit easier, and then we're going to look at the problems. So first you want to highlight or mark on the problem This would be important pieces of information, so numbers that the problem gives you or things that could help you figure out maybe what type of math equation you're going to be looking at or what the problem is asking for. Second, it is typically helpful to draw a picture. It helps you figure out if your answers make sense or not. Third, you want to identify what you're trying to find. And part of that is writing an equation. So at some point we have to convert the problem into math. Fourth, we want to find the critical points. And if you recall, critical points are where the derivative equals 0 or where the derivative does not exist. And then last, we want to answer the question with units. So you need to watch out for this because we have to make sure that our numbers make sense in relationship to the units that were in the problem. And these problems, since they are story problems, they get story answers, which means your answer should be written in a complete sentence. So the first problem is one that you have definitely seen before, or hopefully have seen before. A farmer has 2,400 feet of fencing. He wants to fence off a rectangular field that borders a straight river. There's no fence along the river. What are the dimensions that will give him the largest area? So you hopefully have done these in the context of working with quadratics, and you would have done them by solving them on your calculator or by finding the vertex of the parabola, something of that sort. And so now we're approaching the same problem. We're just using calculus to find the solution instead of algebra. So here, important information if we're highlighting or marking the problem is that we have 2,400 feet of fencing. It's important that the field needs to be rectangular, and that we are trying to figure out what the dimensions are for the largest area. Those are all important things in this problem for us to understand the problem and figure out what we're doing here. So first, if we look at this, we know I'm going to picture here's the edge of my river, and it's very straight. I mean, water is not perfectly straight, but the river itself runs straight. And we're going to put fence right along the river. So I have two dimensions that I'm finding. I want to find the width of the fence and the length of the fence to figure out what that area would be. So here I know that the perimeter of the area around here is going to be 2,400. And I know that in this specific situation it's going to be x plus y. So 2x plus y is going to be the perimeter of what I'm finding, and I know that the area that we're going to make for this rectangular field would be length times width, which is x times y. So at this point I've got two variables. I only want to have one variable. So for me, I can write an equation where I relate these two things together. I know that 2x plus y equals 2,400, so I'm going to say I can isolate y fairly easily, and I can say that y would equal negative 2x plus 2,400. So that's just me taking this 2x and subtracting it over to the other side. And now at this point, I can make a conclusion and say that the area of this field would be x multiplied by y, and instead of writing y, I can replace it with what I solved for y to equal. So the area of the field is going to be negative 2x squared plus 2,400x. Now, if you were in a Math 3 class or an Algebra 2 class, you would graph this in your calculator and you would find the maximum value of that parabola and you would write that down and you would know that that was your answer. So we are basically doing these problems thinking if we were not allowed to use a calculator, weren't allowed to graph it, and it was a requirement that we had to use calculus, what would we do here? So we know that anytime we're trying to maximize or minimize, we're going to have to find a critical point, because those critical points where the derivative equals 0, specifically, not so much where it doesn't exist, but where the derivative equals 0, that means we have a maximum or a minimum value at that point, because it means it had a horizontal tangent line. And so since we are trying to maximize this area, we want to find that maximum value, and we're going to do that by taking the derivative of the area and setting it equal to 0. So my derivative is negative 4x plus 2400, and I'm going to go ahead and set that equal to 0 and solve. So I get 2400 equals 4x, and I'll go ahead and divide by 4, and so that tells me that x equals 600. And I can use a sign chart to double check and just make sure that I am finding an actual maximum, that this doesn't happen to be a minimum value. So if I take my derivative here and I do the derivative multiplied by something smaller than 600, that's positive. And if I multiply it by something bigger than 600, that is a negative. And so based on what we know about finding maximums and minimums, we can say that the graph would be increasing, or the derivative is increasing up until it hits 600, and then it decreases, which means that this value right here is considered to be a maximum value. So if my x is 600, then I want to be able to figure out what my y value is, and so I know that y was negative 2 times x plus 2400, and that tells me that my y value is 1200. So at this point, I've done all the math. I can finally answer the question, and I'm going to say the dimensions that will give the largest area are 600 feet by 1200 feet. All right, next it says a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of metal. So find the dimensions, and we want to minimize the cost. So first, I already went ahead and highlighted and marked on the problem. I'm going to go ahead and draw a picture now. There's my cylinder. And there's the radius, and there's the height. So at this point, we have to identify what we're trying to find and write an equation. So if we look at this, we're trying to find the dimensions of the can. And if you think about how dimensions work for a cylinder, it would be the area of this circle, right? The area of the circle multiplied by the height. That's how we find volume of this. So the dimensions, we might say the radius of the circle and then the height of the can would give us some good dimensions to minimize the cost of the metal. So here, I'm going to go ahead and look for what the volume of the can is. So if you don't remember what volume of a cylinder is, it is the area of the circle that makes the base multiplied by whatever the height of the can is. And they told us in the problem that this is 1 liter. Now that's a volume that is liquid, and we want this to be a volume that is something that we could measure in length or area. So if you were to Google convert 1 liter into and see what the different measurements are, you can actually convert 1 liter into cubic centimeters, and 1 liter actually makes 1,000 cubic centimeters, and so that is the measurement we're going to do. I'm sure you could convert it into cubic inches, but the number would probably not be nearly as nice as centimeters. And the beauty of this problem is that because of the way they phrased it, you could have used any unit you wanted, truly, because they did not. You're not going to be able to write dimensions of a can in terms of liters. That doesn't make sense. So there's our volume. Now we want to figure out what the surface area is. So if you think about that, and the reason I'm doing surface area, it's kind of like what I was comparing with the last problem. We knew that the perimeter and the area would be the two things that kind of work together. Here, the volume and the surface area are things that are going to kind of work together. That's two pieces of information that we can look at, because the surface area is how many materials we're going to use. The volume is clearly what they gave us already. So it's like the last problem, the perimeter had to do with the materials they gave us, and the area was what we were trying to maximize. So our surface area is going to include a circle on the bottom and a circle on the top. And so that's going to be 2 times pi r squared. So that's the circle on the bottom plus the circle on the top. And then if you take the part that makes the actual cylinder shape, the height of that would be 1. That'd be like length times width. That'd be one of those. The other part of this would be the perimeter around that circle, or the circumference of that circle. So it would be 2 pi r. And that might be something, if you guys are confused on how I came up with this surface area formula, we can talk about that in class, where I can actually show you something in 3D and we can kind of look at it. So this is the other formula that we're looking at. And we want to go ahead and just rewrite these so that we're not dealing with two variables, radius and height. We want to just have everything in terms of one variable. So here I'm going to say I've got 1,000 centimeters cubed equals pi r squared times h, and that h would be pretty easy to isolate here. So I'm going to say h is 1,000 divided by pi r squared. And then over here, it's going to be pretty easy for me to just take the stuff for h and substitute it in right there. So I'm going to say the surface area, the thing that I'm trying to minimize, is going to be 2 pi r squared plus my value for h, 1,000 over pi r squared, times 2 pi r. And there's a little bit of simplifying that we can do right here. I can say that this r and one of these r's would cancel out. And I can say that this pi and this pi would cancel out. And so I'm going to say my surface area is 2 pi r squared plus 1,000 times 2 is 2,000. And instead of writing this as a fraction where I'm going to say this is over r, I'm going to write r to the negative 1 power. And the reason I'm doing that is because I'm about to take the derivative of that, and I don't want to have to do a quotient rule. It's just a little bit easier if I use that negative exponent. So if I do the derivative of the surface area, I'm going to get 4 pi r minus, right, because it's negative 1 times 2,000, so negative 2,000 r to the negative 2 power. And this is what I'm going to find the critical points of, because I am minimizing this. So for me to find a minimum value, and we're not going back to Math 3 and graphing it on the calculator to find the answer, we're going to do this by hand using calculus. And so the way that I'm going to find this is I'm going to go ahead and take this derivative and set it equal to 0. Because I know when the derivative is 0, we can find those critical points. So I'm going to say 4 pi r minus 2,000. I'm going to go ahead and put this back in fraction form because I'm not finding the derivative anymore. It's a little bit easier for me to solve it in fraction form. So 4 pi r equals positive 2,000 over r squared, and I want to get my r's to one side, so I'm going to multiply each side by r squared. And that gives me that 4 pi r to the third equals 2,000. And I'm going to go ahead and divide by 4 pi. Divide by 4 pi. And so I have 500 over pi equals r to the third. And so that means my r value is the third root of 500 over pi. So now I'm going to put that on a sign chart. I know that's a nasty number, but I'm going to put it on there just to verify that this really is my minimum value. I didn't do anything wrong. So I'm going to type that in to see what number that actually is, because that's kind of a crazy number. So third root of 500 divided by pi, 5.41. So I'm going to take my derivative and I'm going to type in a number smaller. So 4 pi times 5 minus 2,000 times 5 to the negative 2 power. That gives me a negative number. And then I'll do the same thing with a number that's bigger than 5.41. Gives me a positive number. So that our value, that truly was a minimum. So that's good. And most of us are not going to describe the radius of a can using something so crazy. So I'm going to go ahead and write down that R was approximately 5.419 centimeters. And then at this point, we want to find the height. And so we know that height was equal to 1,000 divided by pi r squared. 1,000 divided by pi times third root of 500 over pi squared divided by pi times, oops, and that gives me 10.839. So now I can go ahead and write my sentence. The dimensions that will minimize the cost are a radius of 5.419 centimeters and height of 10.839 centimeters. And since our video is getting kind of long, I'll let us do the next example in class tomorrow.